नहीं हो रहा शो.
This attract particle. You must have seen that if you don't place it in the middle, it tilts to one side. But when the finger is at the center of the scale, then it gets easily balanced. Many children keep on playing with their pens. Okay, so the weight is considered to act at this point G. Okay, such that the algebraic sum of moments due to these forces about G is 0. Okay, so I hope everybody has understood. Okay, we go to definition of center of gravity. The center of gravity of a body is the point about which the algebraic sum of moments of weights of all the particles constituting the body is 0. The entire weight of the body can be considered to at this point, however the body is placed. Okay, let me bring out a pen. Okay, now suppose this is the body. Okay, so I can consider that it is made up of many small particles. I can consider that it is made up of many small particles, and each particle has its weight, okay, which is acting towards the earth. And since their mass is negligible as compared to that of earth, we consider all of them to be acting parallel downwards. Okay, now the ones which are towards the left of the screen, okay, now the ones which are towards the left of the screen, I'll have to wipe it. I've written on my own face. Okay, I wipe it. Okay, we're back there. Okay, I'll make it this side now. I redo everything. A will generate a anti-clockwise movement this side, right? And the ones which are on the right of the screen, they will generate a clockwise movement this side. Got it? And if it gets balanced, if these all are in equilibrium, then I should have a point somewhere here, okay, where the entire weight of the body can be supposed to be acting. Okay, we represent it with a capital W, and this point is known as the center of gravity. Clear, everybody? Let me undo this and then we read the definition. Okay, so the center of gravity of a body is the point about which the algebraic sum of moments of weights of all the particles. We took just a few. There are numerous, millions of them, and all of them have weight. All of them are directed towards the earth. All of them create a moment. Okay, so if the moments are balanced, if the algebraic sum of these moments is 0, the clockwise is equal to anti-clockwise, which means their algebraic sum is 0. We have already studied that we take anti-clockwise as positive and clockwise as negative. So if they are balanced, their sum will be 0. Then this point about which the algebraic sum is 0 is known as the center of gravity of the body. I hope everybody has understood. I take you to the next slide. Okay, now there are some points related to the center of gravity. The first one is that the position of center of gravity of a body of given mass depends on its shape, that is the distribution of its mass. Okay, I'll again pick up my pen and give you an example. Okay, now suppose I have a pipe. Okay, suppose I have a cylindrical pipe like this, okay, red in color, and when I find out the center of gravity of this pipe, it will be somewhere in the middle over here, acting over here like that. Okay, but as soon as I turn it, and now, oops, I'm writing on my face again, I suppose. Let me undo this. Okay, I'll do it this side. Okay, now as soon as I turn this, okay, and it becomes a ring. Now what happens? Now the center of gravity, which was till now on the mass, is not on the mass, it is somewhere over here, okay, in the middle. Got it? The position of center of gravity of a given body of given mass depends on its shape. So you see the shape changed. It was a rod, then it was in the middle of the rod, in the middle of the axis of the rod, cylindrical rod, and we turned it into a ring, and now it is at the center of the ring. Got it? Everybody understood? So let's read out the example. I erase this. Okay. The center of gravity of a cylindrical wire is at the middle of its length. We just saw it's at the middle of its length. But if the same wire is bent to form a ring, then its center of gravity now is its center, marked over here. Got it? We go to the next slide. Sorry? Okay. Now, the second point is, it is not necessary that the center of gravity always be within the material of the body. Okay, we discussed the last case wherein we formed a ring, and we saw that the ring was not in the material of the body. Okay, it was in empty space. Okay, in the empty space within the ring. So it is not necessary that it will always be on the material of the body. It could be away from the material of the body also. You must have seen a boomerang. Okay, a boomerang looks somewhat like this. Okay, and its center of gravity also is in the air in front of it. Okay, it's not in the material of the boomerang. We move forward. Last one. By the concept of center of gravity, a body of weight W can be considered as a particle of weight W at its center. So if I have this body, okay, and there were many particles, and we consider that now the entire weight of the body is acting on this point. So we can consider this body as a point, okay, a point particle with the entire weight of the body concentrated at this point. Clear, everyone? I hope you have understood. I move forward. Now, this is a section from which you get questions. You don't get many questions from this section. You get just 1-2 marks question, and it is this part from where you generally get the question. In 2014 also we'll do the question at the end of the lecture, wherein you'll get to know the questions were asked from here only. Okay, so if we have regular shapes, if we have regular bodies, then where will the center of gravity of such regular objects or regular bodies lie? Okay, first of all we are taking a circular disc. Okay, a circular disc, it's very simple. The geometric center of the circular disc will be the position where the entire weight of the disc will be concentrated. It will be acting, so the center of gravity of the disc is at its geometric center. If it's a circular ring, okay, it's a ring now. So ring also we have already discussed that now the ring's center of gravity is not in the material, but it is at the middle of the ring, at the center of the ring. Okay, now if I have a triangular lamina, it could be any triangle, so then where will be the weight of the
Sir, we say that we can balance anybody by applying force on COZ, but in case of a ring, it's a COZ in the air.
Yeah, its COG is in the air. A boomerang's also. A boomerang center of gravity is also in the air. It is not in the material. Okay, so it happens. Okay, because after all it's the moments created by the particles of the body which have to be balanced. So if there is a point around which the moments are getting balanced, we'll have the center of gravity there. It's not necessary that the center of gravity has to be in the material. Okay, next we continue to triangular lamina. In case of a triangular lamina, where will its weight act? Okay, so its center of gravity will be at the point of intersection of medians. Now what are medians? Medians are lines which are drawn from a vertex and they bisect the opposite side. If I draw it from this vertex, then it bisects, which means these two sides are equal. If I draw from this vertex, these two sides are equal. So wherever these now meet, okay, the entire weight of the triangular lamina will be acting there, which means the center of gravity of a triangular lamina will be at the intersection of medians. In case of a rectangle, a parallelogram, a square or a rhombus, it's very simple. Wherever the two diagonals intersect, the center of gravity will act over there. Wherever the two diagonals intersect, the center of gravity will be there. Okay, now we go to solid or hollow cylinders. If it's a solid cylinder, which means it could be a thick rod or a thick wire, okay. So we have done such questions when we did principle of moments. It is always at the center of the axis. It is always at the center of the axis. Okay. So midpoint of the axis of the cylinder. It is the midpoint of the axis of the cylinder. Again, whether it is solid, if it is solid, then it is in the material. If it is a hollow cylinder, then it is in the air. Okay. So in case of both, whether it is a solid or a hollow cylinder, in both it is on the point. And if it is again a solid or a hollow sphere, okay, if I have a solid sphere and on the other hand I have a hollow sphere, in both these cases, again the geometric center will be the point where the center of gravity will act, okay, where the center of gravity will lie. Okay, now the solid cone. If I have a solid cone, there's slight difference between a solid cone and a hollow cone. If it is a solid cone, then its center of gravity will lie at a height which is h by 4, which means suppose its height was 8, so it will lie at 2, it was 8 centimeters, so it will lie at 2 centimeters above the ground from the base, okay, on the axis from the base. On the other hand, if it was a hollow cone, then it would lie higher. Now I divide it into 3 parts and a little higher. So it would lie at h by 3 from the base of its axis. Clear to everyone? If it's a solid cone, then it lies at h by 4, okay, which means 1 by 4th of the height, okay. On the other hand, if it is a hollow cone, then it will lie a little higher. Sorry, beta?
Why it is only divided by 4?
That will derive and tell you. That's geometry will derive and tell you. Okay. We move forward. Okay. Now, center of gravity and the balance point. I've already discussed that many a times we try to balance the scale or we try to balance the pencil and it does not balance, but when it comes to a particular point, then it balances. We have done some numericals also related with the scale and weights. Okay, so if it is a scale, okay, oops, just a minute. Okay, so if it is a scale of half a meter, which means this side I have 50 centimeters and this side I have 0 centimeters, then we say that it will perfectly balance at which mark? Which mark will it perfectly balance? I put a knife edge, and what mark should it balance? Tell me quickly. What mark should it balance? It will balance at 25 centimeter mark, which means the midpoint. We have done numericals, isn't it, related to that. Now here in this figure, it is not at the midpoint. This is a meter scale, which means this side we have 100 centimeters and this side we have 0, and the knife edge is placed at 60. Okay, so what happens? Let me undo this. So what happens, that we know that the entire weight of the body, it could be considered as a point which is acting at 50 centimeters, okay, which means the body will turn anti-clockwise, okay. And so to balance it, I need something which can counterbalance it by creating a clockwise movement, and so we bring in these weights. We have done numericals like this, right? So a uniform meter rod can be balanced at the 50 centimeter mark. A half a meter rod can be balanced at the 25 centimeter mark, and so on. Okay, it will always be the middle. We move forward now. Till now we have talked only about uniform bodies, okay, where will the center of gravity of uniform bodies lie. Now suppose it was a non-uniform body which with an irregular shape, then how do I know where is its center of gravity? Okay, so we can determine it. How do we determine? Suppose this is the body, we make three holes, okay, one over here, the other over here, and the third one over here or there, okay. Now what do I do? I hang it through a pin. I hang it through a pin such that it is free, okay. I'll just tap it and check that it is moving freely, and if it is freely moving, then I'll let it come to rest. Once it has come to rest, I use a plumb line. A plumb line is something which the masons use. मिस्त्री दीवार बनाते हैं तो आपने देखा होगा वो plumb line use करते हैं so that the wall is straight up, okay, it doesn't get slanting to one side. So we use a plumb line on the same needle, and then we draw a line, okay, parallel to the plumb line we draw a line, okay. Now once we have done this, we remove the irregular piece from that hole, and we put it to the second hole, the B hole. We again ensure that it is free to move, and then we let it come to rest. We let it oscillate and come to rest. Once it comes to rest, we again use the plumb line from the same needle, draw a line over it, okay. So we get three lines. Wherever these three lines intersect, that gives me the center of gravity of this irregular body. Let's read it out quickly. Okay, what do? The way is, we make three fine holes. We suspend lamina along the plumb line using a pin from point A. It should be free to oscillate. When it comes to rest, we draw a line along the plumb line. We repeat by suspending from point B and C, where the three lines intersect. Spellings of intersect are wrong, okay. There, that is the center of gravity of this irregular body. Clear, everybody? No doubt in this. This was a very short, simple topic, and we have covered it, okay. You can leave your queries in the box and I'll surely answer them, okay. Now we go to some previous year questions. So the first one is from 2014, and herein they are asking, what is the weight of a body at the center of the earth? Okay, this is a class 9 question, I suppose. We studied this in class 9. They had put it up in ICSE 2014 also, okay. So what will it be? Can somebody answer? Anybody answering? No? Chalo. It'll be 0, okay. It will be 0 at the center of the earth. The weight of the body placed at the center of the earth is 0, since the value of G at its center is 0. We know that G is capital G m1 m2 by r square, okay. So here distance becomes 0, okay. It will be 0 since the gravity at the center of the earth is 0, so its weight also will be 0. Second question they ask is, the position of the center of gravity of a body remains unchanged even when the body is deformed. State whether the statement is true or false. This we have already done that example, okay. The example was of a rod and then bending the rod to form a ring. We saw in both the cases this had the center of gravity at the midpoint of the rod, and here now it comes at the center of the ring, okay. So as soon as the shape changes, the mass distribution changes, immediately the center of gravity also change. So if the body is deformed, which means its shape is changing, okay, then if the shape is deformed, if the shape is changing, definitely the distribution of mass changes, and if the distribution of mass changes, then the center of gravity has to change. Let's check the answer. Okay, the statement is false. The CG changes when shape of the body changes. That's what we said, that it is not true. The CG has to change. So the statement is false. The center of gravity changes when the shape of a body changes. Right, we move forward. These all are easy things. Everybody's understanding easily. Right? We go to next question. Okay. Okay, now this while discussing I had told you, where does the position of center of gravity lie for a circular lamina, a triangular lamina, and a uniform ring? This is a 2011 question. So we have studied this. Where does the center of gravity of circular lamina lie? Answering, not answering? No answers. I'll give it. Okay, it lies at the geometric center of the circular lamina. Okay, triangular lamina. Yeah, somebody's answering. Bhagat, tell me, what are they telling? Triangular lamina, the point of intersection of the medians. The point of intersection of the medians. Okay, then a uniform ring. What have they written? Tell me. In the center of triangle, no. It is actually the intersection of the medians.
Point of intersection of median.
Who was that?
Intersection of median, a lot of people.
Lot of people. Chalo. So many of them have got wrong, excepting a child who wrote the center of the triangle. Please don't write center of the triangle. Write the intersection of medians of the triangle. And if it's a ring, again it's the geometric center. Okay, we go to the next question. Okay, first one is geometric center, second one is at the point of intersection of its median, and third one is at the center of the ring. So most of the children have replied correctly. Very nice. We go to the next one. Okay, this one says, this is not related to center of gravity. It comes from a little earlier topic, couple. Okay, 2019, which means last year. Last year it was asked, define couple and state the SI unit of moment of couple. What's couple? A girl had called up one day. She had sent me a WhatsApp also. She wanted to know. She was not understanding a term related to this. So let me see if somebody can come up. Define couple. How many forces do we need to make a couple? 2, right? The 2 forces. Okay. What else do we need? Okay. They should be parallel and 2 equal opposite parallel forces. But they are not acting along the same line. Got it? The line, they are not acting along the same line. Let me pick up my pen. They are not acting along the same line. Okay. If one force is acting this side, the other one is parallel. Okay. So it is acting this side. So both of them are same. If this is F newtons, this also is F newtons. So 2 equal forces. They are opposite. One is acting in that direction, the other is acting in this direction. They are parallel. And their lines, if this is the line of action of the first 4, the other line is parallel. They are not acting on the same line. They form a couple. Okay. How did we find moment of a couple? What was the formula that we studied? It's not asked in this, but let's just revise. What was the formula? Can somebody quickly write to me? What was the formula for moment of a couple?
Pair of forces formed by external force, the force of reaction.
No, give me the moment of couple. How did we find the moment of couple?
Force into perpendicular distance.
Okay, I have got 2 equal forces. So either of the force into the couple arm equal, okay, one of the forces into the couple arm. What is couple arm? Couple arm is the perpendicular distance between the two forces, right? So if I get moment of a couple by multiplying a force with a distance, what should be its unit? Quickly, what should be its unit? Answering?
Newton meter.
Excellent. Who's that?
Piyush Kumar Gupta.
Which Gupta?
Piyush Kumar.
Piyush Kumar Gupta. Excellent, Piyush. That's the right answer. It will be Newton meter, the SI unit. Okay. I go to the next slide. Let me undo this, otherwise it will become permanent. Okay. So we go to the SI unit of moment of couple is Newton meters. Piyush has already answered. We can do a question. Okay. Now this again is principle of moments, but we have got center of gravity also over here. So I have put it over here. Okay. A uniform meter scale is in equilibrium. Okay. It's in equilibrium, which means that the scale is balanced. Okay. The scale is balanced. They are showing us a weight which is suspended at the 5 centimeter mark. They are showing us a weight which is suspended at the 5 centimeter mark. Okay. So it must be creating, let me pick up the pen. Pick up the pen. It must be creating a anti-clockwise movement, right? Which means something is balancing it. What is creating the clockwise movement? Answer quickly. What is creating the clockwise movement? Okay, as time is already up. We are 3 minutes over time. Okay, but I'll finish it. One more question. I finish it. Quickly answer. What is creating the clockwise movement? No answers? Chalo, I gave it. It is the weight of the meter scale. And where is it acting? It is a meter scale, 100 meters. So its center of gravity will be at the fifth. Sorry?
Shingarika.
Shingarika says what?
Long distance.
Huh?
Long distance.
Long distance? No. Sorry, Shingarika. It will be acting at the center of gravity. Okay? The weight. The center of gravity is at 50 centimeters, which means the weight of the scale is causing the clockwise movement, which is balancing the anti-clockwise movement, and hence the scale is in equilibrium. Got it? So they ask us what is the weight of the meter scale. Got it? So we need to find out what is the anti-clockwise moment. What is the anti-clockwise moment? Who will answer quickly? 40, 30 minus 5, 25. 25 fours are 100, 1000 GF centimeter. Anybody answered? No? Chalo. So the anti-clockwise moment is 1000 GF, which means I have to have the same clockwise moment. My clockwise moment also should be 1000 GF centimeter. Got it? So what is the distance at which the weight of the scale is acting? It is 50 minus 30, which means 20. Okay, so 20 into W should give me 1000, right? Which means W is equal to 50 grams. Who gave the answer 50 grams? Okay, very nice. Children, you are doing well. Okay, you got so many holidays all day you can get to study. You should practice numericals in this time, and your results will definitely be better. Don't just lose on your studies. Stay home. Okay, very nice. Piyush gives the correct answer. Sorry?
She's actually Shingarika.
Okay, that's Shingarika. Shingarika, you are giving the correct answers. Congratulations. Keep it up. We go to the next one. Solution. Okay, so there's the solution. 50 GF. Anti-clockwise moment should be equal to clockwise moment, which means 40 GF into 30 minus 5 should be equal to W into 50 minus 30, which means 1000 GF centimeter should be equal to 20 W, which means W is equal to 50. Shushingarika gives the correct answer. Congratulations.